Afternoon mga alagan. So someone sent me this picture, or he asked me first. He was asking, is it okay if the post was relocated 16 inches away from the original location of the post, but still within the footing area? Is it still okay for the footing? So basically, what they had was this. This was the original location of the post, and then they decided to move it. I don't know the reason why. It could be maybe they just added or increased the width opening, or it was installed in the wrong spot. So basically, they cut this column here and then transferred it on this side, and then just added this plate. And he said this is 16 inches from the original location. So I would say if that is relocated 16 inches and still within the footing area, so probably the footing is at least 36 inches. So if this is your footing and then this is your original column location, if this is 36 footing, so this would be 18. This is 18. And then if you move the post 16 inches, so you still have 2 inches from the edge. The center line of the post would be 2 inches from the edge of the footing. So I would say at least the footing would be at least 36 inches. Now he was asking, is this still okay since since the column is still within the footing? That's not. I mean, I cannot answer yes or no right away without doing some analysis. But I will not be in this video. We will not be discussing like the design of the footing itself, but we will discuss the consequences or the implications if you relocate your column away from the center line of the footing. So if you are not restrained by the location or the location, because sometimes if you are, I mean, this one obviously this is with or at least inside the basement area, so it's not along the property line where you will be forced to have a what do you call this one, like a um eccentric footing. So for example, in some instances you have your, if this is your building, say one side is at the property line. Now you have nothing to, I mean, you have no other choice but to have your, say if you want your column right at the property line, then your footing would be that one, like eccentric. But if you are in the middle and like of your floor area, there is no reason why, or it is recommended to have a footing um, or column centered with the footing, so that, so if this is your footing and then this is your post, so it is always recommended to have that column centered with the um, footing, so that you will have a uniform bearing pressure. Now, if you move this load away from the center line, um, say for example right here, what will happen is it will increase the bearing capacity on one side like that. So your equation now would be P over A plus minus M over H. This plus minus depends on the eccentricity if you are within the kern limit. So usually if this is your so this is your footing. So if this is your footing, and then this is your center line. You will divide this one into six segments, or yeah, one, two, three, one, two, three, and then this one. This is most of the time this is referred to as middle third. So as much as possible, if your resultant of the load is within this location within the middle third, you will have a um, trapezoidal bearing. If so, for example, if your eccentricity is within L over 6, this is L over 6, this is L over 6, L over 6, L over 6. So if your E is less than L over 6, then you will have a trapezoidal um, bearing pressure distribution. If um, if your E is equal to L over 6, you will have it triangular. And then if E is greater than L over 6, what will happen is you will have an uplift on one side. So what will happen to your bearing pressure would look like this one. So you have an area here which is basically lifted, and that amount will just be added to this increase here in bearing capacity. I mean, if the resulting bearing pressure is still less than the bearing capacity, then that's fine, regardless of what's the eccentricity. If even if the new load will be right at the edge, this one. If the resulting bearing capacity is, or required bearing is less than the bearing capacity, then it's still okay. But the implication of that, if you have eccentric load, is you will have, so this is your maximum and then your minimum bearing capacity. So if um if the resultant is outside the middle third, then what will happen is there will be cases that the resulting equation will be P over A minus M over S, and then this will result in a net uplift on this. Like your Q minimum would be P over A minus M over S, and then Q max would be P over A plus M over S. That's your Q max, and then so the increase in bearing here due to eccentricity is if that value is still or exceeds the bearing capacity, then it is considered failed. So let's go back to the situation here. So what happened? So if this is your footing now, this is your center line, and this is offset. Your eccentricity is equal to 16 inches. Now your original P. So the equivalent load diagram on this one would be let's draw it on this side here. So if you have your footing and then your load is right here, P. So this eccentricity is 16 inches. Now, because of this eccentricity, you are now introducing a bending on your moment. So this load is actually equal to, if you have a footing here, so that will be equal to a load at the center. At the same time, you have a bending moment. So your moment is equal to P times the eccentricity. So what causes this moment is the P times E. So basically what happened is in the original load diagrams, you have eccentric load. So if you um, add, so what we do usually is, so you add a P here, and then you also add another P going up. So basically, you add P downward, and then you add P upward. This will just cancel out, so it doesn't change the load um uh diagram or the loading. What it does is basically you just transfer the P at the middle, so you can utilize the P over A in the equation, and then the moment plus minus M over S. S is the section modulus of the footing. So basically P times E, this one, this load P is this one here, this one. So that's the load P, and then this P going up and P going down. This is the one that created the bending in this direction, the rotation. So it will rotate clockwise. So that's why we have a moment here, clockwise M, which is equal to M of equals to P times E. So if you move, so for example, this is 100. So this is P is 100 or 1,000 pounds for the sake of discussion. If that P is 1,000 pounds, so the resulting force would be P, which is 1,000 pounds, and then your moment, which is 16,000 photons. So you are now introducing a moment which was not originally considered in the original design of the footing. So what happened now is because of this footing, you will have a, at least, or if this is within the middle third, then you will have a triangular or trapezoidal distribution. So instead of the regular, you know, regular bearing pressure here, which is P over A, uh, just a different color. So instead of the original bearing pressure, which is P over A only, and it's uniform, because of the centric load, you are now introducing this, you are now adding this value here. And this is the Q max, and this is the Q min. Now, if the resulting bearing capacity, this new Q max due to eccentricity, if this is less than the bearing capacity, the bearing pressure, uh, usually in a project there is a geotechnical investigation, and then they would recommend the bearing capacity. Now that is the value that you will compare this Qmax with. If there is no geotechnical investigation, some building codes would have recommended the values for different soil types. In our case, if there is no geotechnical investigation, we we will safely assume a 15,000 or 1,500 PSF or 75 kPa bearing pressure, bearing capacity. Now, for example, there's an geotechnical investigation, and the bearing capacity was only, say, 2,000 or 3,000 PSF. Now, if this is the bearing capacity, and because you move, so for example, 1,000 pounds, then divided by um, 9, because say assuming the minimum dimension was 36 by 36, because when they move the column 16 inches, he said is still within the footing area. So if the load is 1,000, for example, it's really small. So, but for the sake of discussion, so if P is 1,000, P is 1,000 divided by A, which is 3 times 3, the resulting bearing pressure there is 111, which is really small because we assume it smaller, 1,000 pounds, that's nothing. But if that is say 20,000 or 20,000 or 30,000 pounds, then that's really significant load. So assuming this is 111 pounds, now if the resulting so imagine this is only 11,000 pounds versus 3,000 pounds, and then if you introduce a bending moment, for example, for the sake of discussion, this is now 3,250 because of the eccentric load. Now it is now um, bigger than the bearing capacity. So if it exceeds the bearing capacity, then it's considered failed, although it's not really. I mean, uh, theoretically, it already failed, but with all the the technical resistance factors and then your load factors for your dead load and live load, maybe it's still fine. But for this, theoretically, it's already considered failed if you exceed the recommended bearing capacity. So that's why if possible, really avoid um, eccentric loading. So I told him that what will happen is if you move the column away from the center line with footing, this is what will happen. You will increase the bearing capacity, and it might exceed the allowable bearing capacity. But since there is no geotechnical investigation, and I told him like it's really difficult to know because there's nothing to compare with. Even if we can calculate this one like this P over A, the Q max, we will never. I mean, there's no way we can compare it, or there's nothing to compare it with because there's no technical investigation. So if you otherwise you have to do it so we can confirm it's really okay or not. And he talked to the contractor, and they just decided to cut this whole thing and then pour a new pour a new footing. Um, Basically a new footing so that the new column location will be in the center of the new foundation. So that was the agreed solution. But although yeah, it can be checked, but without soil report, I mean you can calculate how much is this new bearing capacity, but what if the actual bearing capacity is, say, we assume 1,500 and then the actual is only 1,000? So it will be useless without doing something like investigation. And then doing that investigation, it costs money. So I don't know, like maybe 5, 10 grand. So if you, and then it's not a guarantee that it will be okay. So instead of doing that, they just decided to um, cut this slab and then pour a new footing. So he asked me this one because it was flagged by the inspector, and then I told him like, if you just have if you just fill this hole here before the inspection, it would have been probably okay. And he was laughing. So yeah, yeah. So again, this is the consequences if you move a footing or a column away from the center line of the footing. So it could still be okay, but without doing soil investigation and then do a proper calculation, we will never know. Usually in new construction, if uh, um, there's situation where you don't have no choice but to have an eccentric load is, for example, if this is your property line, and then for some reason, if you get approved with a variance to construct a house right to the property line, so your building footprint will be here as well. There's no setback or whatever. So if you have your post here or column, right? So if you have your column here, you have no other option but to have a eccentric footing. That one. So if there is a column in the mid, like right here, then that would be good because all you have to do is run a tie beam. This one, tie run a tie beam. So what the tie beam does is, like say, this is your footing, right? And then this is your column, right at the edge of your footing because this is the property line. Now, in previous in our earlier discussion, we mentioned that if you have a centric load, all you have to do is transfer it. So if this is your load P, right? So transfer that load P here. So if this is load P and this is you will add another P also. You will counter that with the same load P. So technically, you're not adding anything because you added a P downward, but you also at the same time you're adding P upward. So your new loading would be this one, and then the moment due to this load like couple, so it will create a bending counterclockwise. So the new loading diagram for your footing because of the eccentric load, the new loading diagram would be this is your new imaginary. So original location was here, but this will now be your imaginary column location, and then at the same time you have your moment here. So this is your P, this is moment E, or moment which is equal to P times E, and this is your eccentricity E. Now, what like during construction, what's like the easiest solution if there is a um, column, say there's another footing here. All you have to do is run a tie beam here, strong enough to resist, to have a at least moment capacity, resisting moment of your tie beam, at least equal to this value here. So what will happen is your load P, you will have a uniform bearing pressure due to P, the relocated P, and then the moment due to eccentricity, which is P over A, will be resisted by this tie beam. So if that beam, um, if the capacity, I mean, you design the size of this beam based on this load, right? So this is your, uh, basically, this is your applied moment MA, and then you will equate that with the resisting moment, and then calculate it, you calculate the section based on that um, what do you call this one, based on the moment. So your section will be, this is B and D, and usually this B um will be set the same as the column width. So the only unknown is depth. So from the base right here, this is your only unknown, and then that should solve the issue of having an eccentric load. If not, if there is no way you can have a tie beam because there's no column in the middle, your other solution would be considered a rectangular footing, and it will be really big. I tried this before. This one, it will look like that one here, and it will be really thick because it would require a deeper or a longer footing in this direction. And then if the load is right here, then you would have bigger bending stress, so you have a thick footing and then more rebars, and then um, the yeah, you will need this big area in order to minimize the bearing capacity or bearing pressure at this corner, and it should be less than the allowable bearing capacity given by the or recommended by the geotechnical engineer. So I hope this is clear. Um, if you have other questions, just let me know and we will address that in the next video. Thank you.